Hello everyone. In this video we will continue to examine topic 7.2 nuclear reactions, and in particular we will continue to unpack the concept of nuclear binding energy. In the last video we walked through how the nuclear binding energy was defined and exactly sort of what kind of energy it corresponded to. That is the difference between the energy of the bound nucleus as compared to its constituents considered alone, right? That extra energy is known as the binding energy, the energy required to separate a nuclide into its constituent nucleons. Now, consider for a second the difference between the binding energy for a small nucleus like this helium shown here, and a large one, like iron, or even very, very large, like uranium. What is your instinct about how much energy it would take to separate a nuclide like iron 56, which is 56 protons and neutrons, compared to the energy it would take to completely separate a helium nucleus? Well, if your instinct is that it takes more energy, you're absolutely right. Okay, so it takes a lot more energy to separate completely the constituent nucleons of a nuclide of iron or anything with more nucleons. But we could ask a different question, okay? One that sort of gets at what will ultimately be super revelatory for how the world works, which is, instead of asking how much binding energy there is for that iron 56 or the uranium-238, for example, you might instead ask, well, okay, in order to get that iron 56 or that uranium-238, what I really want to know is, what is the binding energy, not full stop, but per nucleon that's required, right? In other words, like, is it more efficient to have a whole bunch of these guys floating around? Can I get more energy if I have a certain pile of nucleons by having lots of these bound systems or just a single 238? I want to know how efficient it is. And the answer to that particular question can be found in the chart of the binding energy per nucleon. And this is, with no exaggeration, one of the most famous, most important charts in all of physics. Ultimately, I'm going to argue that the classic version, which is the one shown here, is upside down. But we'll get to that at the end. So this chart shows the binding energy per nucleon, not the total binding energy of a nuclide, which inevitably goes up as you get bigger nuclides, but sort of how efficient it is as an arrangement of nucleons. This graph tells you the answer to the question, how much energy do you get out if you have millions of nucleons by arranging them all into helium or all into iron or all into uranium, okay? And what we can see is that the curve, which you should probably be able to sketch by hand by the end of this, gives a very clear relationship with increasing nucleon number. So as you go up an increasing nucleon number, right at the start, right at H1, okay, the binding energy per nucleon is 0 because that is simply a single proton, so no binding energy required. But then as you go up in nucleon number, you have a very sharp spike right at the beginning to that helium-4 nuclide, and we'll talk about that in a moment, as well as sort of all the way up until you reach a maximum at iron 56 or nickel 61. They're very close together right at the top here, and then it sort of trails off in this direction. And what this means is that iron 56 or nickel 61 is basically the most binding energy per nucleon that you can have. So it's the most binding energy for a given number of nucleons that you can get. This is the most efficient arrangement of those nucleons, and we'll talk about why moving forward. Now, every single one of these elements, every element along this curve, okay, along the whole curve, shown sort of in more detail on the right here, is, in fact, greater than 0. And what that means is it takes some amount of energy to pull them apart. That it is still always true that the arrangement of nucleons where they are bound together in the nucleus gives them a smaller mass than the arrangement of those same nucleons spread apart. But if you had sort of a certain number of nucleons spread apart and you asked, well, how much energy do I get if I let them combine, this chart gives you the answer to the arrangement you would want to have them in to get the most energy out. That's what that iron 56, nickel 61 is all about. In the next video, we'll continue to sort of discuss the implications of this chart. But before we move forward, I would strongly suggest that you just take a very close look at it. You should probably be able to sort of sketch the general structure by hand, including the spike at helium, which we will talk about in the next video.